Hello everybody, and welcome to CIV 398, assignment number 3. So as you guys will see with assignment number 3, it's actually not too bad. It starts off really simple, question 1 as you guys have seen, and it gets a little bit harder, but it doesn't stay too bad. Until question 5. Question 5, I'm pretty sure you guys won't like me for what I do to you guys on question 5, but the rest of the assignment is pretty nice, easy. It should be a nice, easy week for you guys. At least that's my hope. So again, just like the other assignments, we're going to have these nice little assignment videos to hopefully guide you along. So in this video, we're going to be covering question number 1. And as you guys will see, question number 1 is very similar to assignment 2. And what question 1 says is consider the symmetric matrix. So the key here is that this matrix A that we're given is symmetric. Now, quick note, I noticed that my version of A has a bunch of zeros. I checked random variations and you guys will not have all these zeros, or it's possible that you guys don't have these zeros. So this is going to be a symmetric matrix, but there's the chance that all the components are non-zero. So it makes it a little bit more complicated. And we have 3 questions that we need to solve for this matrix A. And the first one is determine the eigenvalues and their corresponding eigenvectors. And you're saying, Clayton, come on. This was assignment 2. I'm an expert at this. This is going to be no problem. And as you guys will see, a lot of my slides for this particular part are reused from assignment 2 because the process is exactly the same. But then part B and part C, that's where things get a little different. So part B says find an orthogonal coordinate transformation matrix Q such that M prime in the new coordinate system is a diagonal matrix. And, oh, Clayton, well, this is a bit new. You lost me. I remember the coordinate transformation matrix Q. I remember that we can find M prime using Q. But what is a diagonal matrix? Well, that means that the diagonal components of this M prime are going to be non-zero values, or some of them could be 0 values, but the rest are 0 values. So for instance, if I were to look at matrix A here, and if A was diagonal, then those negative 2's, those would be 0, and those positive 3's, those would also be 0 at the end. Now, final part of the question says find M prime in the new coordinate system. So if we look at part B and part C together, we're saying, well, this is basically just a transformation change of basis sort of question where we just go M prime is equal to QM times Q transpose. But what happens here is even though it looks kind of bad, because we remember that doing that calculation, it's a little time consuming. We say, oh, it's a lot of work. But what we'll actually find out is that because this is a symmetric matrix, there's a very unique property that allows us to solve this very fast and very quickly. So let's go into the first part of the question, which was the eigenvalues. So if you guys remember eigenvalues, we need to solve the equation the determinant of m minus lambda I is equal to 0. So we got the first option by hand. So if we define a matrix M as a 3 by 3, then we say, okay, well, all we do is we take the determinant of m minus lambda I is equal to 0. So if we look at this, m minus lambda I, well, it's the same as matrix M, except we're minusing a lambda on all 3 of those diagonal components. So if we kind of expand this out, the determinant equation, we get a big, yucky cubic equation. No one wants anything to do with it. And what was nice about assignment 2 is that we had simplifications. A lot of these values inside the matrix were 0. That allowed us to solve for it pretty efficiently. However, I didn't really see any simplification in your guys' matrices. So what we're going to have to do is we're going to have to solve this cubic equation. And since it's cubic, we know that there's going to be 3 different eigenvalues. So that's all we have to do. We have to solve this cubic equation for the 3 eigenvalues. But I know that you guys are thinking, solve it by hand? Well, that kind of sucks. I'm going to use Mathematica. So just like before, we can define our matrix M in Mathematica and use the function eigenvalues of M to instantly get those eigenvalues. So it'll save you guys quite a bit of time. And use Mathematica while you can, because even though it's possible for the rest of the assignment's more generated in a way to make it more of a do-by-hand assignment rather than throw it in Mathematica assignment. So for the eigenvalues, one thing I want to add, because this was kind of the biggest question I got asked was, Clayton, I got my eigenvalues from Mathematica, I input them into the assignment, and my assignment says I'm wrong. So the trick is to remember that the assignment asks you to list the eigenvalues in a specific order. So in this assignment, the eigenvalues have to be inputted in ascending order. So my smallest eigenvalue to my largest eigenvalue. Every single time a student approached me saying that it's saying my eigenvalues are wrong, they had it in the order from largest to smallest. So please be careful in which order you're inputting those eigenvalues. It will mark you right or wrong based on that. So even though your eigenvalues are correct, it is important that we recognize the order they must be inputted in. So after that, we can go on to the eigenvectors. So to determine the eigenvectors p, we need to solve the equation mp is equal to lambda p. So just like before, we can kind of write out this equation. If we look at the right-hand side here, we see that a1, a2, a3, b1, b2, b3, c1, c2, and c3. Well, that's our matrix M. We already know that. That's no problem. Lambda, those eigenvalues, we know all those too because we just solved for them. So our only unknowns in this is going to be p1, p2, and p3. So what I can do is I can create three equations. Oh, that English is really bad. Creates three equations. I just sound kind of funny when I say that. But anyways, we got three equations. And if we look, we have three unknowns, which are the P1, P2, and P3. So theoretically, three equations, three unknowns, we can solve for them. However, as you guys remember, for eigenvectors, there's going to be infinite solutions. So before I just said assume P3 is equal to 1. Well, as Dr. Sammer pointed out, which is a very good point, I can assume a value for P1, P2, or P3. It doesn't always have to be P3, and it doesn't always have to be 1. The key is just you pick one of those and you assume a value. So personally, I pick P3 is equal to 1. So once I do that, I can say, okay, I can create two equations now, or sorry, I can use P3 is equal to 1 and solve for P1 and P2 using two equations. Because now I got two unknowns, just P1 and P2. I got two equations I can solve. And what I'll end up with is my eigenvector is equal to P1, P2, and 1. Now the key here is that this is not normalized. Now, if I remember the assignment correctly, when you're putting your eigenvalues, it doesn't care if it's normalized or not. I don't believe it specifically asks for normalized eigenvalues. However, this is a very important concept when we start talking about the orthogonal matrix Q that transforms it. So please keep in mind this little tidbit that it's not normalized, because we'll talk about that later. So again, if we're looking at the equation above, we have lambda in there, and we have three different values of lambda. So we're going to have to repeat this process 3 times, each with a unique value of our eigenvalue, lambda. But again, you guys are saying, Clayton, that's too much work. I don't want to have to deal with that, and I don't blame you guys. 3 by 3 matrix kind of sucks. So we can just go into Mathematica, define our matrix, and use the function eigenvectors of M to quickly solve for the 3 eigenvectors. So now we're going to talk about symmetric matrices, because that first part, like I said, that's just review. You guys are laughing at it. You're going, Clayton, eigenvalues, eigenvectors. I'm the expert. No need to tell me how to do it. I already know how. So now we're going to talk about the second part, which was having to do with that coordinate transformation matrix Q that results in our matrix M turning into a diagonal matrix M prime. So let's recall that if the eigenvectors P, Q, and R of a symmetric matrix M, so the key here is symmetric matrix M, are used as the coordinate transformation matrix Q, the result will be a diagonal matrix, and this is where all the kind of the bells and whistles go off in your head saying, oh wait, that's what part B was asking for, diagonal matrix M. And this diagonal matrix M will consist of the eigenvalues of M. You're saying, Clayton, that's too much English. I don't like English, I prefer math. What exactly does this mean? Well, let's look at our transformation equation. M prime is equal to QM Q transpose. And what this statement says is that if I choose Q as my eigenvectors, so I got P1, P2, P3, Q1, Q2, Q3, and R1, R2, and R3, then my my M prime after this transformation will be a diagonal matrix. So notice how only the diagonal components have values and the rest are 0. And the value of those diagonal components will be my eigenvalues. So if we look at question C where it wants that M prime, well, we can already know that the values are just going to be my eigenvalues. So technically, I don't even have to do any math or anything special like that. After I find those eigenvalues, I can just substitute them in. Now, I guarantee I will get asked this a lot, so I want to make this very, very clear. And this goes back to that normalizing my eigenvectors. When we do these coordinate transformation matrices, it's very important to remember that Q is an orthogonal matrix. An orthogonal matrix. So if I were to take Q as my eigenvalues that are not normalized, I will get the answer wrong. So it's very important that we take Q as an orthogonal matrix. Therefore, all those eigenvectors that you guys found, even though it marks them correct as the eigenvectors up top, when we're inputting them as Q, we need to make sure that they are normalized. It's very important in this step to make sure that those are indeed normalized, or else the assignment will mark you wrong, because let's be honest, you guys are wrong. If you guys do that, it is wrong, because Q has to be an orthogonal matrix. So that concludes question number 1. I hope I cleared up any concerns that you guys may have. Again, not a very hard question. You guys are saying, oh, Clayton, this is assignment 2 from last week. I'm an expert, and that's great. That's what I want to hear. I want to know that you guys are understanding the material and that hopefully this is easy to you guys. I don't want this to be a challenge. So thank you guys so much for listening. I will see you guys in question number 2.